So good afternoon, ladies and gentlemen. My name is Sri Sundari Ratnasi. I'm from National Research and Innovation Agency of Republic of Indonesia. I could say that I'm the least experienced related to the radionuclide monitoring system because actually my background is more into like a nuclear fuel management or like more into the reactor. But here I just would like to talk about the possibility for how the recent development of the new generation of the reactor can also have the impact for the radioxenon release or radioxenon monitoring system. So, so I will talk about how the molten salt reactor off-gas system efficiency and its possible impact on radioxenon release trajectory estimation. So this is still like again a preliminary assessment, even though I already did it in the past, but it's still like the continually of it, but still a lot of work to do. So as we already know that nowadays, the one of the small modular reactor, which is called molten salt reactor, is one of the most progressive development in across of the globe, which this reactor of the molten salt reactor, it potentially to release the radioxenon, approximately it can reach between 10.10 becquerel per day until 10.13 becquerel per day. Meanwhile, the conventional of the nuclear power plant, it approximately only reach between 10.9 becquerel per day. And also one of the most progressive of the molten salt reactor, it's being built in China and it's already being operated since 2004. Here, so we already see here that there is the molten salt reactor. It's called TMSR-LF1, which is located in Wuwei, and it started to operate it since October in 2023, but it reached full power in June 2024, and they also demonstrated online refueling in October 2024. And it also planned to scale up, even though it's still like a pilot plant, but it also, if it works well, they plan to scale up the power from the 2 megawatt thermal into 60 megawatt thermal. Meanwhile, in other countries, they also start to develop it, including Indonesia, which is work together with a private company from United States, the Tarkon company. They also plan to build a molten salt reactor in Indonesia, and also there are some countries such as Canada and Denmark also working together with the South Korea. They also try to build this type of the reactor. So let's get to know a little bit more about this TMSR-LF1. So as I already mentioned, it's the type of the liquid fuel experimental reactor. So this kind of reactor, basically, they use the fuel with the uranium-235 dissolved in the salt and with the thorium in a blanket for the breeding. And since we are focused in this study about the trajectory estimation plots, we need to know the coordinate of this reactor. And it is located about 38.5 in the north and 102.36 in the east. And why is it important related to the xenon emission? Because this reactor, it has the type that it has a continuous fission gas handling system. While most xenon and krypton are stripped from the salt, fraction can still escape through the off-gas line. And this makes off-gas system efficiency a critical factor in whether radionuclides can be detected at the CTBT international monitoring system. So where the transport exists, of course, the off-gas efficiency can be or could be become the key control for the detection. So basically, this study, it provides a preliminary estimation of the radioxenon transport from the TMSR-LF1 molten salt reactor in Gansu province, China, following its full power operation on 17 June 2024. And the trajectory analyses are applied to approximate the atmospheric dispersion of xenon release and their potential arrival at nearby IMS radionuclide monitoring station, such as based on the location. So there are like RN20 around Lanzhou, and RN20 around Beijing, RN21 around Lanzhou, and RN38 around Takasaki, Japan. And the role of the off-gas system efficiency is also examined, as it is critically influences both of the scale of xenon emission and the probability of the detection. So basically for the methodology, this is like, as I mentioned before, that this is a very initial assessment. So we use the trajectory modeling using the open source of the high split with using the period within 17th until 22 of June. So based on the first full power of the operation and with the integration 120 hour, and how this is going to be impacted for the stations nearby, such as RN20, RN21, and RN38. And by using the very simple statistic, we also try to analyze for the relative detection index, which we use the calculation from the frequency of the trajectory and also with the half-life of the xenon. And this is like the result from the high-split trajectory plots. As we already know here, that that's the star one is the resource of the TMSR-LF1, and then the dot on the red one, that's the approximate RN20. So it's just for the sensitivity test. We tried also to create it with the different heights, even though it's not the real heights of the stack of the reactor, because it needs like the clear design of the stack of the reactor. So here we continue more into like how is the impact for the RN21, RN20, and RN38. And in this case, with the different height between 100, 300, and 500 meters, the most possible or likely it's going to be impacted on the RN20, which is located in Beijing. And others that the occasional impacted will be in RN38. It is located in Japan, but still like the most consistent ones will be impacted into RN20. And how is it the efficiency of the off-gas system related to the possible of the detection index? So we use the simple calculation to multiply between the efficiency and also the frequency of the trajectory and also the half-life. In this case, we know that the fraction release with the smaller fraction release, which means the efficiency is high. So with the efficiency is high, then the release of the xenon is low, and then the detection on the station is going to be like also low. So in conclusion, the off-gas system efficiency is one of the key factors that can be considered, and also with the higher efficiency, therefore the minimal xenon escape, and with the low efficiency, the stronger IMS detection potential. And from the high split modeling, it shows that the highest transport probability to RN20 and RN38 is only the occasional, and RN21 could be minimal or even undetected. And by combining off-gas release fraction, transport frequency, and xenon decay survival, it offers a dimensionless measure of relative detectability. And the results show that RN20 consistently yield RDA value cross efficiency scenarios, particularly under longer release duration and low off-gas efficiency. And it also indicates that the result highlight how MSR off-gas system affect MS background and CTBT monitoring confidence. However, as I mentioned, that this is still the initial assessment, so there are still many limitations and further research you need to do. One of them is like about the source strength. So this one multiplied to 10.10 becquerel per day. This is from the simulation that already existed from the previous studies, but this is only the simulation. So the real one from the pilot plant of 2 megawatt TMSR-LF1, actually it's not being public yet for how much actually the source or the release that they can produce there. So therefore, the specific fission yield data, which is not publicly yet, it needs to be known. And then consider to the first day of the full power, which is on June 2024, it demonstrates the worst-case timing of the plume transport. Meanwhile, we know that xenon inventory builds up during the operation. Therefore, the future work should extend the equilibrium conditions. And also, as I already mentioned before, that the chosen heights here is between 100 and between 100 and 300 should be there. It's just for the sensitivity test. Meanwhile, the actual stack for the TMSR-LF1, it should be like around 30 until 50 megawatt. Therefore, the more robust simulation should use the real design parameters once it's available. And another thing is about the transport times and decay factor. So the transport time to the IMS station, the RN20, RN21, and RN38, they are not explicitly shown. Therefore, the future work should quantify the decay correction for each station transit time. This is the references, and thank you so much for your attention. If you have any question, or I'm very much welcome for the input or any suggestion for this research, because this is like still a very initial assessment, and I'm pretty much still new in the radionuclide monitoring system. Thank you.
Thank you, Sundari. This fantastic presentation. Thank you. There's time for questions.
If I may. So this is for MSR, where I think off-gas is a very important issue. But then, of course, you have other types of reactors. I mean, in the region, I'm sure there will be other types of reactors, especially in China. So do you see a difference? Is there a signature between multi-salt reactor versus other type of reactors, or are you going to investigate those issues?
Yeah, so basically, why did I choose the molten salt reactor? Because the first one, this is the most progressive one that really make the progress among other the small modular reactors that any other countries try to develop. And then the second one, because it has like a really critical of the off-gas system. So everything related to the off-gas system, even the power they generate, the fuel that they burn up, it can be detected through the off-gas system. So that's why I choose the MSR. But I need still to do more research related to the small modular reactor in another types. But so far I choose this one, it's because this is the most progressive one, which is really already operated among two other small modular reactors. Mm-hmm.
Yeah, there's a question. Yeah, it's a question.
Thank you very much for your presentation. I appreciate it very much. I might have missed it. So you said you did the I-split simulation, and you looked, and I noted your result. RN20 will be most impacted, RN38 occasionally. I wondered how long have you looked at 1 year or so 1 year of data?
No, it's just only approximately for the 120 hours, so it's a very short. Okay. That's why I still need to further research to do that.
Okay, thank you very much.
That. Yeah.
There's one more hand.
Thank you. My question is about mechanism of generation or increased generation of xenon 133. In normal light water or heavy water reactors, it's released the major nuclear reaction is iodine, which decays to xenon. And what is the reason that this reactor releases much more? Maybe iodine is activated by neutrons, or what? You understand the question, the nuclear reaction? Thank you.
Yeah, thank you so much for this question. It's pretty much almost the same like the conventional reactor, but however, for the molten salt reactor, they already the burn up of the fuel itself, it's almost like not really 100%, but it's much higher than the conventional reactor. So that's why it's going to create more xenon or more release of the xenon instead of the conventional reactor.
Thanks.
No more questions? No. Oh, there's one in the back. Yeah.
So I think that the MSR off-gas system purpose is to remove quickly the xenon from produced in the core, and one could assume that xenon 135, that is a strong absorber of neutrons, will therefore be at slightly higher concentration relative to the other isotopes and isomers in this off-gas system. Did you look at the ratios as well, or?
Not yet. It's still just xenon 133. But thank you so much for this input. It could be like another consideration for further research.
Okay. One quick question. The last, by Christian.
So thank you very much. What I didn't really get, you said at the end you did not account for decay. So on your last slide, so during Bloom transit, you said you did not account for decay.
So I only used the half-life only. It didn't like pretty much the exact decay for every transport.
Okay.
So it still needs like further research. Yeah.
Thank you.
Good. Thank you very much, Sundari.
Thank you.
Thank you.
Very-